Hi everyone, it's great to see you in this video. Have you ever wondered how scientists can find planets really far from Earth from a few light years to hundreds, thousands, or even billions of light years while still being able to determine their distance, size, mass, composition, or even predict what's happening on their surface without ever setting foot on a planet like Mars? In today's video, we'll help you answer all those questions. Welcome to Real Fact. The first question is, how are planets found? Unlike a star that can emit a strong light, most planets don't glow, or if they do, their light is too weak compared to that of stars. In fact, scientists very rarely find an exoplanet through telescopes in the same way you can see Earth from Earth. All exoplanets found directly through telescopes are newly formed gas giants. They glow because they are still very hot and are usually far enough from their host star so that their light is not dimmed by the star behind them. Most exoplanets are discovered indirectly through the phenomenon of a star dimming as the exoplanet passes in front of it. When a planet passes in front of a star, it partially obscures the star and dims its brightness. Scientists monitor the brightness of many stars at the same time. And when a periodic dimming occurs at a particular star, that's when they identify the existence of an exoplanet. This method is called the celestial transit method. It sounds easy until you realize that the dimming of a star during a transit of planets is extremely small. For example, consider the Sun. A transit of a Jupiter-sized planet would only reduce the apparent brightness of the Sun by about 1%. For an Earth-sized planet, the reduction in apparent brightness is only 0.001%. Requiring extremely precise measurements. In contrast, transit observation not only helps detect exoplanets, but also allows scientists to determine many of their characteristics. Based on the time interval between repeated transits, we can calculate the orbital size of the exoplanet. Orbital size indicates the distance of the planet from its star. The smaller the orbital size, the closer the exoplanet is to the star, and vice versa. The distance between a planet and its star also indicates whether the planet is in a habitable zone, a region warm enough for water to exist on its surface. Based on the dimness of the star, we can calculate the size of the planet that has passed by it. Even more amazing, we can even study the atmosphere of an exoplanet during transit. Of course, if it has an atmosphere, specifically, a small amount of the star's light will penetrate the planet's atmosphere during transit, causing dispersion. Light dispersion is the phenomenon in which a beam of white light emitted from a star or other light source is split into multiple beams of light of different colors. Based on the specific degree of dispersion, scientists can deduce the composition of the atmosphere. From the atmosphere composition, scientists can deduce the composition of the protoplanetary accretion disk from which planets are formed, or in other words, the composition of exoplanets. The atmospheric composition, along with the distance between the planet and its star, plus the star's temperature, all help determine the planet's surface temperature. From this, conclusions can be drawn about whether the planet's surface is pleasant and suitable for life. According to NASA statistics, as of 2020, more than 4,000 exoplanets have been discovered, of which nearly 200 were found through planetary transit observation. Nearly 800 planets were found using radial velocity. The remaining 200 exoplanets were discovered through 7 different methods, which I cannot fully present within the scope of this video. The second most common method after planetary transit observation is the radial velocity method, also known as the oscillation method. The oscillation method is usually only applied to massive gas giant planets that are very close to their stars, often referred to as hot bursts. Jupiter is hot because it has considerable mass and is also close to its star. Its gravitational pull on the star can be described as quite significant. It causes the star to orbit it to some extent. Seen from afar, the star appears to be swaying back and forth due to gravity. And when a star moves back and forth in front of a telescope, the light emitted from it undergoes the Doppler effect. When an ambulance speeds past you, the sound waves from its siren are compressed at the front of the vehicle and expanded at the back. As a result, you perceive the siren louder as the vehicle approaches you and quieter as it moves away. Similarly, light waves are compressed as the star approaches the lens and stretched as it moves away. For light waves, being compressed means they turn blue, also known as the blue shift. Stretching, on the other hand, means turning red, also known as redshift. The recurring blue and red shifts in the light emitted from a star indicate the presence of a massive planet orbiting nearby. The greater the blue and red shift, the faster the star is swinging. The greater the swinging speed, the greater the mass of the planet orbiting it. Based on the star's mass and the degree of wobbling caused by the gravitational interaction of the two bodies, the mass of the exoplanet can be calculated. And that, ladies and gentlemen, is the method of flirting. Wait a minute, sir. Based on the mass of a star? The mass of the star is unknown. So how can we rely on that? Oh, I almost forgot. The mass of an independent star is calculated using the gravitational lensing method. Imagine you are standing on Earth observing a distant galaxy. Between you and that distant galaxy lies a black hole, because black holes bend space-time around them. When light from a distant galaxy reaches this region of space-time, it is also bent. In this scenario, the black hole acts like a gravitational lens, bending and magnifying the image of the galaxy behind it. As a result, an observer on Earth would see a distorted image of the galaxy as a ring or halo surrounding the gravitational lens, which is the black hole. This is known as the gravitational lensing effect. By precisely measuring the degree to which a star bends light, its mass can be calculated. This refers to binary star systems, which consist of two stars orbiting each other. Scientists measure the orbital size, orbital speed, and orbital period to calculate the precise mass of each star in the system. Oh, what about the distance then, sir? How can we know the distance of an exoplanet if it's many light years away from us? The distance from exoplanets to Earth is, relatively accurately, the same as the distance from their host stars. A planet is typically located anywhere from its star, ranging from a few million to several billion kilometers. This size is insignificant when considering that a light year is already 9.46 trillion kilometers long. And exoplanets can be anywhere from a few light years to 12.7 billion light years away from us. There are several methods used to measure the distance from a bottle of Earth to stars in the universe, depending on the distance of the star. This applies to stars that are nearby, within a few thousand light years of us. Scientists use the parametric method. Simply put, parallax is the change in the position of a relatively close object relative to a more distant object when you change your point of view. It may sound confusing, but parallax is actually something very easy to visualize. Hold your thumb out in front of you, close one eye, and notice the relative position of your thumb to objects behind it, such as a window, a picture on the wall, or a tree. Then try with the other eye. Is that good? Your thumb appears to have shifted position as you change your viewing angle. However, the distance from your eyes to it actually remains unchanged. Replace your left and right eyes with the positions of the Earth in its orbit around the Sun, and your thumb with the star you want to observe. Apply geometric formulas, and you will be able to calculate the distance to the star. For more distant stars, where parallax methods are not applicable, scientists use a series of interconnected methods, collectively known as cosmic distance leather. First, humans discovered standard candles. Standard candles are astronomical objects with a defined absolute luminosity, such as variable stars or Type 1a supernovae. Scientists use two values, absolute luminosity and apparent luminosity of a star, to calculate its distance. The distance between standard candles serves as a metric for measuring larger distances in the universe. Absolute luminosity is the brightness of a celestial object when it is placed at a standard distance of 10 times its passing value, approximately 32.6 light years. Apparent luminosity is the brightness of a celestial object as observed from Earth. Besides parallax and cosmic distance scales, there are still some other methods for reading distances that we couldn't fully explain in this video. See you in the next videos. Let us know your thoughts by commenting below. Are there any methods you'd like us to add that we're currently missing? If you enjoyed this video, don't hesitate to like and share it. And Don't forget to subscribe to the channel and click the bell icon to always receive notifications about new videos.